Hi, everyone. So 2 years ago, Lucid Vision was the first company demonstrating a working prototype of an RDMA-enabled 10 gig cameras here at Vision in 2022. Since then, we have now released RDMA capability for any 10 gig camera that Lucid provides. However, it was never our intention to keep that as a proprietary standard, and we've worked with other industry partners in the past 2 years to make it the next open standard for high-performance 10 gig camera and beyond. We'll explain in this presentation the benefits we see for that. Just a few words about who we are. Lucid Vision is a camera manufacturer, machine vision camera manufacturer of 2D and 3D cameras, all of them based on the Ethernet GigaVision technology, available at 1, 2.5, 5, 10, and now 25 gigabits. We have over 100 unique camera designs as of today, with all our product designed and manufactured in Canada. Our headquarters is in Vancouver, Western Canada, and we have satellite offices in US, Germany, China, Japan, and other countries. Let's start with a bit of timeline on the GigaVision implementation. GigaVision is based, as you know, on the Ethernet transport layer, with the first protocol introduced in 2006. GigaVision 1.2 GigaVision 2.0 was introduced in 2011, providing support for non-streaming devices, let's say light-enabled controller, GigaVision-enabled light controller, and also higher speed network, including 10 gig, in addition to the support for precision time protocol, IEEE 1588. 2018, the GigaVision standard was expanded for the transmission of more complex data structure, multi-part data structure, such as 3D data. And the latest official revision is version 2.2, released in 2022, with one of the main improvements being the support for GenDC, generic data container, which provide a self-described data container to transmit arbitrary data. We're now looking at the next step of the GigaVision standard, and once again, we turn to other industry to leverage industry-proven network protocol that can be adapted to our industry, machine vision industry. So we look at remote DMA capability. Remote DMA is a way to transmit over a network to a receiving device with bypassing the CPU and OS entirely on the receiving end. We're looking at InfiniBand and its later iteration, RoCE V1 and RoCE V2. That's a high-performance, low-latency network fabric that has been adapted by the high-performance computing cluster, the high-performance computing industry. And it provides a way to transmit very fast data inside a computer or between computers. However, InfiniBand is not a network protocol in the sense that it cannot leverage the existing switching infrastructure. In 2011 and then 2004 and 2014, sorry, it was expanded with RoCE V2, which is remote DMA over convergent internet, which provide routing capabilities. And that has now been announced as being part of the next GigaVision standard, GigaVision 3.0. That's a screenshot from the A3 Association, the trade association that hosts the GigaVision standard, that announced that the next release will support RoCE V2. This is being discussed right now. We expect this to be published next year. To understand more the benefits of RDMA in gig camera application, we first need to understand the current limitation of the UDP-based technology. When GigaVision was introduced in 2006, it was focusing only on 1 gigabit device. And for simplicity and efficiency, it was decided to adopt it on top of UDP. UDP provides a way to transmit packets with very low latency, but with very few quality control, very few flow control. All quality control is added on top of this on the application layer. So the application needs to monitor packets, track for missing packet, ask for resend. That enabled camera manufacturers to release very quickly and be very efficient in their implementation. However, it's pushed the burden of the reliability and transmission entirely on the application side, which increase the burden on the host side and the CPU. Between 2006 and now, we've seen a rapid innovation in the machine vision industry. At this time, when GigiVision was introduced, most camera systems were still lower resolution, slower frame rates. We've seen in the last 10 years the acceleration of the pace of innovation with newer sensor, faster sensor, higher resolution, and in turn, the need for higher bandwidth interface. On the application side, the complexity of task and the demand on the backend system has increased as well, where in the past, a lot of systems were relying on a few number of cameras and a more typical topology. We now see variety of tasks, variety of topologies that are being deployed, which push even more burden on the application side. And so the challenge we face today with UDP, as explained, any reliability feature is pushed back on the host side. So when everything goes well, the packet gets transmitted, they get received, and everything runs smoothly. However, as soon as a packet is detected as missing, the application needs to issue a retransmit request to the sender, to the camera. The camera needs to interrupt its current transmission, fetch the packet from its frame buffer, retransmit the packets. When the network starts being congested, that can come from various reasons, but most of the time it will be on the host side. The host cannot process the incoming packet fast enough. We see a kind of domino effect. The first missing packet is retransmitted, another packet gets missing, another packet gets retransmitted. We end up with a bottleneck, and we end up with missing frames in that case. We do have 10 gigi network, 10 gigi system working today with camera, but we end up having to overspec the host to handle the corner case when we have those bottlenecks happening. We propose to provide a way to better manage the demand on the system. And for that, once again, we look at what's been done in other industries. Luckily for us, there are tons of people working with enormous amount of data. For many years, it's the data center and high-performance computing industry. Those guys have been working at much faster speed than 10 gigi, and they have developed those technology to achieve that. Starting with the InfiniBand in 2006, and its further iteration, Rocky V1, Rocky V2. It's what we now propose to apply to our industry. The core benefit of those remote DMA protocol is there is no CPU involvement on a per packet basis. There is, once the image data streams, the CPU disengage, the OS disengage, and the data stream is directly pushed to the host memory in a dedicated memory area. If you want to picture the current UDP implementation, at every transmission, for every packet, the packet has to be recopied at multiple stages, from the transport layer driver to the socket to the application buffer. At each time, this involves context switching, this involves CPU load, and if you were to picture that as a highway with a toll booth, when there's not too much traffic, there's enough lane open, everything runs smoothly. However, as too many packets come, the toll gate, in this case the CPU that needs to decode all those packets and sort them and put them back in contiguous memory, can become the bottleneck, creating essentially a traffic jam. Now with an RDMA stack, we can stream directly from the host to a dedicated memory that has been pinned, a memory on the host that has been reserved for the transmission. The host channel adapter, the network card, will receive those data and push them in order in a contiguous memory, with the key benefit for the application that it's working with complete image data. It doesn't have to decode data, it doesn't have to push back data together. It will receive only full buffer, with all the flow control and all the quality of service handled at the host channel adapter. How does that work in practice for a Gigi system? Sorry. First step is the hardware required for that. You need a camera that adapts this technology, of course. You need a host channel adapter. It's not any kind of brute force. It's making sure the chipset, the network chipset, can support this protocol and implement it. So we are not relying on lots of buffers or dedicated resource on the hardware network adapter directly, just making sure this protocol can be supported. And typical Cat6 cable and the Windows or Linux OS driver required for that. In practice, how the transfer is initiated, the driver will pin a memory space on the host side. It's a registered memory space, registered buffer, that will be provided to the network card to access. After that, the OS completely disengaged for managing where this memory is going. And then the transfer is controlled by what is called queue pairs. Queue pairs is a way for providing a connected transfer where the camera and the host channel adapter create those transmission and completion queue that will monitor the transfer and provide a concept of credit in the sense that the camera will not send to the receiver until the receiver signals that it has a buffer available for reception. The building block for that on the host side are the Verb API, on Windows Network SPI, Network Direct SPI, and on Linux the libverb APIs. Those are supported by most network chipset vendor, Intel, Marvell, Broadcom. However, for some of them, it's mostly dedicated to their server infrastructure. It's much easier to find a Rocky V2 enabled adapter on fiber 25 gig, 50 gig than it is on 10 base T copper-based PoE card. But there are a few, and we selected a few Broadcom for our own implementation. But that's open. That's an open standard, so it will become available as well as it's become more popular for more industrial solutions. The change we had to do on the packetization for the Gigi implementation is the way the packets are encapsulated. In UDP, each and every packet contains a header that is used to track the position of this packet within the image, within the buffer. The application with each packet it receives needs to track this header, identify the packet ID, and place it in the right memory. That provides for lower network efficiency. We have to add some encoded data with each of the payload data. By adapting RDMA, we can get rid of that. There's only one leader with the initiator packets. After that, all packets are transmitted without any GVSP header, Gigi Vision Stream Protocol. Instead, we have this packet sequence number that is implemented as part of the InfiniBand packet that is, which is the blue one in this one. That's essentially, that will be tracked on the hardware level. The network card will track those packet sequence number and make sure that data is received in order. If the next packet is missing, it will simply signal to the sender, the camera, to stop the transmission and hold until this packet gets transmitted, and then copy it in the right memory space. Now for some benchmark of UDP versus RDMA. As I said earlier, we are delivering 10 gig camera working over UDP still today, and we have customer implementing it. We end up having to make sure the system is kind of beefy to handle those corner cases where there's too much demand on the host and packet decoding can become trouble. That's typically the type of configuration we will use. Here we're comparing running 4 10 gig cameras at full speed in UDP with an average CPU load of 538%. That's just receiving the data. There is zero processing, no display, nothing. Compared to UDP, where we have, on average, with the same configuration, same system, less than 1% of CPU load to handle this over 30, in that case, 35 gigabit of data. One key part with adopting this new network technology is the topology we can support. Of course, point-to-point technology is supported. Many-to-one, which is a multiplex way, is as well supported, and it's actually making it easier because of the low-level flow control. If any one of you ever had to run multiple gigi camera on a shared network through a switch, there is no requirement anymore to deal with packet delay, with packet transmission delay. All of that is managed on the flow control side with the sender just holding until they have enough credit to transmit their data on the network. Those two technologies have been tested, have been validated. Lucid has application notes showing how to deploy those. we are working on the next step, which is how to stream to multiple computers. We are losing one key feature by adopting RDMA compared to UDP is multicasting. Because of the connected nature of the RDMA transmission, we cannot use multicast. However, there are other opportunities leveraging some of the GenDC capabilities to transmit the data in different ways, managing those transmission flow, as they are called in GenDC. It could be implementing daisy chaining in the sense where the camera streams to a first computer over RDMA, and the next computer has another RDMA computer to other daisy chain computer. If we transmit the full image, of course, we will double, triple, quadruple the latency. However, there are ways to truncate the image in smaller chunks and start the daisy chain transmission before we receive the complete buffer, which will control the latency differently. The other option is this one-to-many transmission. Same thing. If we were to transmit full image to 4 different computers or 3, we would have to double, triple, or quadruple the bandwidth demand. But for many applications that needs to distribute the processing, they don't really need to have the full image on every computer. Typically, an AOI system will have a stripe of the image with maybe some overlap. Using these GenDC capabilities, we can initiate multiple transmission flow, where part of the image will be streamed to one computer and part of the image to another computer, which will enable to manage the latency more finely. Of course, streaming all data to all computers at once is multicasting, which won't be supported with RDMA, but we don't think it's a core requirement for many systems. And now a quick summary of lucid current implementation. As I mentioned, we had the first prototype 2 years ago. We've now released this to all 10 gigi and 25 gigi camera Lucid produces. Once the new GigiVision standard 3.0 will be released, we'll make sure that our implementation is compliant with that. We are 99% compliant anyway, but we will make sure that as soon as it becomes available, we support officially this Gigi 3.0. Today, we have a range of 10 gigi cameras. The just newly announced Triton 10, it's a compact IP67 camera for extended temperature and harsh environments. The Atlas 10 camera, which is also PoE, 10 gigi RDMA, this one supports larger sensor, up to 35 millimeter, 65 megapixel global shutter. And we've just announced at the show this week our range of 25 gigi camera with, of course, RDMA, with direct LC connection, in the sense we don't need to use an SFP module. We have adapted this function of the optical transceiving. We can connect the optical fiber directly to the camera, which saves on cost, size, power consumption, and improves signal integrity. As I mentioned before, finding 10 gigi adapter for PoE cards with copper connection is not the easiest thing, because most of the ecosystem is data center based and optical based. So we have released our range of 10 gigi copper based adapter, a 2-port standard, a 2-port PoE, and we've just announced a 4-port PoE adapter, PCI Express 8, with individual isolation of each PoE stage and individual control of each PoE port. We can turn on and off programmatically every one of the 4 PoE ports. And on the 25 gigi side, we have SFP adapter from Broadcom that will support RDMA as well. Lastly, the next step beyond that, we solved the issue of transmitting to the application memory, to the host memory, the computer RAM, without any CPU involvement. However, we know that more and more applications rely on GPU-based processing. And there are technologies, in this case, NVIDIA GPU Direct technology. It's really designed for application to transmit from one GPU memory to another GPU memory, bypassing the OS and CPU, but we can leverage the same thing to stream directly into the GPU memory. That's the next step we're working on. It won't be part of the Gigi 3.0 standard, but something we already have internal prototype running like this. There are some specificities between Windows and Linux implementation, but that's the next step we're working on with this. With RDMA, as we believe, being really a building block for the future expansion of high-speed Gigi technology. That's the end of my talk. If you have any question, I think we have time now. If not, we're in all 10 booth E40.
OK, thank you very much. Big applause. Thank you. Are there any questions? Because we have room for questions. If there are no, there's a question.
Someone there.
Hi, thank you for your talk. I just want to have more insight on the complexity of development and the price also for such a development.
So on the camera side, there's no hardware impact. Actually, we had our 10 gig camera, the Atlas one, that were on the market for many years. For us, it was simply a firmware update. The engineering cost was quite high for us, especially we were championing this thing and we were the first mover. But really, we wanted this to be an open standard, so now it's being codified, it's being standardized by the Gigi working group. But yeah, you have to support that on the firmware side to implement this protocol in the camera side. On the host side, yes, our driver had to be adapted. We actually provide a GentL interface for our transport layer driver, so if third-party software want to use our Arena SDK driver just for the RDMA, we have this GentL interface. But yes, that has to be developed. But there is no hardware change. The board themselves, I forgot to mention, but the 4-port card is €700. The 2-port PoE is 400. It's essentially the same price as any 10 gig adapter. It's just making sure we have the right chipset that adopt this protocol and that can handle the requirements of RDMA.